Imagine a world without machines. Imagine no cars, no trains, no airplanes, no agricultural machines, essentially no manufacturing, no generators, therefore no power, therefore no electricity. Now imagine future civilizations looking at the present today and thinking how primitive it is, the same way that we would look at the past without machines. That future is upon us. And the reason for that is there's a confluence of several technological innovations that will greatly increase the capabilities of future machines. And with the aid of my little friends here, I'm going to tell you about one of the key enablers for this coming machine revolution. And it's called feedback control. Okay, so first let me tell you a little bit about the ingredients that go into this new breed of machines. The first is our ability to harness power for mechanical work. And to put this in context, we're going to have to go back about 250 years to the dawn of the first machine revolution, the Industrial Revolution. And when we think of a canonical example from this era, it would be the steam engine. Here was a machine that could produce thousands of watts of power. It had incredible influence in our lives. And these machines were huge. They were the size of a room. They weighed thousands of kilograms. Now I want to make a comparison with this machine over here, the one that you just saw flying a little minute ago, and in particular, this little motor here. It's a rare earth magnet motor. Now this motor can produce tens of watts, but if you normalize its power capabilities by its weight, it can basically produce 5,000 times more power than a steam engine. Said a different way, if you could shrink the size of a steam engine so that it had the same weight as this little motor here, you need 5,000 of them to produce the same amount of power as this little motor over here. That's quite impressive. The second ingredient is computation. Let's go back about 70 years. There was a project called the Mathematical Tables Project in the United States, which employed hundreds of people to create mathematical tables. These tables would be used in scientific and engineering enterprises. In fact, some of you may even remember textbooks that had these tables at the back. Full disclosure, I remember having those textbooks myself. Hundreds of people would sit in a warehouse and would be separated by mathematical tasks, addition, subtraction, multiplication, and the really talented ones, division, and they would work together to create these mathematical tables, sines, cosines, logarithms, etc. Fast forward to today. In your pocket, in your purse, in your briefcase, you have more computational power than everyone in the world combined. Okay? The mobile phone that you have has more computational capabilities to do arithmetic tasks than 7 billion people in a warehouse. Just that little computer that you have in your device. Okay? The third ingredient is sensing. And for this, I'm not going to go that far back. Our group has been working on quadrocopter vehicles for quite a long time, about 15 years. We started building this one about 10 years ago. It's huge. Okay? Each of these motors can produce 1,000 watts of power. That's more than the power produced by a horsepower. Why so big? Well, it turns out that the driving factor for the design for this device to be so big was this unit over here, the inertial navigation system that sat in the middle of this box. This device sensed accelerations and rotational rates of this vehicle. And it was instrumental in making this thing work. And this is how big it was. It weighed 1 kilogram. This isn't actually it. This is a wooden replica of it. Fast forward to today, and again, I'm going to use the example of your mobile phones. In your mobile phones, you have the equivalent of this. In addition, you have cameras. You have magnetic compasses. Okay? You have GPS receivers. Okay? All consume absolutely low power. And that's the reason why, instead of having something this big, nowadays, you can have something that's this size here. You can see it here. This thing actually flies. You can buy this. It costs $50. Okay? And it's only in the last 10 years that we've gone from this to something like this. It's quite incredible. So we have these three things which have greatly allowed us to broaden the scope of what machines can do. Okay? We can design machines now that can sense almost anything. We can bring to bear huge amounts of computation. And we can act on the results of the computation to affect the world because we've been able to harness power. But there's one thing that's missing, one key ingredient that's missing. And in order for me to talk about that, we have to go back back to the Industrial Revolution and the steam engine. So here I have a diagram. Hopefully some of you can see this, people at the front. This is a picture of a Boulton and Watt steam engine, the size of a room. Now, one of the reasons why this was so disruptive at the time, not only was it more efficient and able to produce more power, but it could do something rather simple. It could run at a constant speed, irrespective of the steam pressure, irrespective of the mechanical load, irrespective of environmental changes. And the reason it could do that was because of this very clever little device here called the flyball governor. And here's a blow-up of the flyball governor. Okay, here it is over here. Okay. How does this device work? You basically had two balls that would connect it to a spindle and would rotate. And the rotation rate of this device was slaved to the rotation rate of the steam engine. So if the steam engine went faster, the flyballs would rotate faster. Okay? If there was a mechanical disturbance which resulted in the machine to speed up, these things would rotate faster, centripetal forces would make them fly apart, and due to a mechanical linkage, the aperture controlling the amount of steam that entered the steam engine would be reduced, which in turn would have a tendency to slow the machine down. The same argument would apply when the machine slowed down. The restorative mechanism here would force it to speed up. Okay? Clever device. The problem is that it was difficult to make it work, especially across a different range of machines. Sometimes the machine would grind to a halt. Sometimes the speed of the machine would increase uncontrollably and the thing would damage itself and destroy itself. Other times the speed would oscillate, also resulting in damage. This was a real problem, and it caught the attention of the greatest physicist at that time, and probably one of the greatest physicists of all time. The same person that unified electricity and magnetism and therefore light, James Clerk Maxwell, of Maxwell equations fame. In 1968, he wrote this seminal paper where he tackled the problem of instability of governors and steam engines, and he presented it to the Royal Society. The paper was called On Governors, and I have a page from this paper right here. Okay, don't worry, we're not going to go through the equations. Okay. This was revolutionary at the time. He was able to come up with mathematical tools that would predict the stability of governors and steam engines by just looking at geometric and physical properties of the system, lengths of linkages, masses, etc. For some configurations, he would be able to come up with closed-form equations, and this was great for designers. They would know ahead of time how to hook up the governor to a steam engine to ensure that it was stable. For more complicated equations, he wasn't able to solve it in closed form, but it motivated a whole bunch of engineers and mathematicians to use those relations to come up with conditions of stability for these classes of systems. And this was basically the birth of control theory, which is the science of feedback control. This is the missing ingredient. You can have all of these great things, but if you don't know how to put them together in a stable way, you can't make them work. And this is what I want to talk to you about today, is feedback control via several examples. Okay. With the aid of these flying machines, I'm going to demonstrate several important aspects of feedback control. First, let me describe the system. The vehicles themselves are relatively straightforward. They have, in fact, let me pick one up here so you have a better chance to see me point to things. It has 4 motors. It allows us to produce thrust, rotation rates, roll, pitch, and yaw. There's sensors in this unit, the equivalent of one of these, and a computer to close the feedback loop. There's another feedback loop in the system, and it consists of these cameras, which is basically an indoor GPS system. That information is sent to several computers, which run our algorithms, that process the data and generate decisions, and then commands are sent back to the vehicles via wireless communication. Next, I'm going to give you a demo on the importance of computation and why you need sufficient computation in order to do something like this. Right now, this outer loop is running at 50 times per second. What I'm going to do is I'm going to artificially tell the team to lower the rate at which this thing receives commands. And let's see what happens. Okay, so right now it's at 50. Let's go to 40. Let's go to 30. Let's go to 20. Let's go to 10. Let's go to 5. Let me get out of the way. Okay, and we recovered back there. Okay? So the take-home lesson here is that if you're going to run feedback loops, you need to run them at a sufficiently fast speed, which means that you need a sufficient amount of computation. By the way, this is kind of a similar instability that you would observe in a flyball governor. And another point to make is this is the kind of stuff that we teach our undergraduates when we teach them the fundamental of basic control theory. It's not that complicated to predict this type of instability. Another strength of a model-based control design is the fact that you can come up with rigorous guarantees of when something is going to work. So in this demonstration, we're going to show you how we use models to design complex tasks for vehicles. How does model-based control design work? We build a mathematical model of a system using physical principles, things that you would study in electrical engineering, mechanical engineering, computer science, mathematics. And then once you have a physical model, it's actually straightforward to figure out how to modify the model to achieve a different task. For example, let's say that not only do we want the vehicle to fly, but we want it to do this. We want it to balance a pendulum. Okay? So we would augment the physical system to include the dynamics of this pendulum. Then we would apply tools from control theory to tell us what mathematical relations there should be between the things that we sense and the things that we control to guarantee stability and performance of the system. So I'm going to go ahead and do that here. Okay? And here you see the vehicle reacting and balancing the pole. It's a little bit jittery. Okay? Now, I put the pendulum in a little cup. The cup is just preventing the bottom from sliding off, but other than that, it's not providing any constraints, and you can see that if I give it a little nudge. Okay? Now, one of the strengths of this approach is not only that it can do this, with some slight modifications, I can broaden the scope of this demonstration to tell the vehicle to go to a specific point in space. Okay? So here, not only is the vehicle balancing the pole, but it's also going to where I'm telling it to go. Needless to say, it'd be physically impossible for a human being to do this. Okay? Now, it almost looks like it's not really balancing the pole. It looks like it's glued to it. You will see that that's not the case when we basically stop the demo and the pole falls off. Another strength of model-based control design is that you can come up with one algorithm that works over a broad range of circumstances. Okay, so what does that mean? It means that we don't have to go to a computer and split the space up into, if the vehicle is doing this, do this. If it's doing something else, do something different. Again, the process is the same. We come up with a mathematical model. We apply control theory tools to tell us what relations there should be between what we sense and what we actuate. And that algorithm works, irrespective of the state it finds itself in. For this demonstration, okay, I'm going to take this vehicle. The control system has been turned off. These propellers are just idling. And I'm going to throw this vehicle into the space, kind of like I did at the beginning of the talk. When the vehicle is above a certain height, about 3.5 meters, the control system will switch on. Okay? Now I'm going to do this over and over again, and I'm going to throw it differently every time. The vehicle is going to find itself in different situations every single time, yet the same algorithm works no matter how I throw it. Okay. So it's extremely robust. This is extremely powerful. Means that we can just design one set of control laws and it works no matter what the circumstances are. As we have seen so far, mathematical models are extremely useful for designing control systems that achieve difficult tasks with guarantees on their stability and performance. But they can also be used for something else, and that's adaptation and learning. In this next demonstration, we are going to have a vehicle perform an extremely acrobatic task. It's going to hover in the center of the space, and then it's going to execute an extremely fast triple flip. Now, it does this so quickly that it is impossible to use feedback. Okay? There just isn't enough time for the system to react. This is analogous to a figure skater doing a triple axel, or a gymnast doing a vault, or a diver executing somersaults. Basically, once the maneuver is started, there's nothing you can do. It's all muscle memory. So we're going to do the same thing here. We're going to use models in two different ways. The first is to give us a rough idea of what a triple flip should look like. And I say roughly because it is simply too difficult to capture with mathematical models exactly everything that's going to go on when this thing does a triple flip. The aerodynamics alone are too complicated. Okay? So after this initial guess, we're going to observe how the system performed the maneuver, and we're going to use the first principle model to guide us, guide the algorithm to change what it did so that next time it does a better job. Okay? Let's see it work. Okay. The problem with that is that the first time it did it so well that we're not going to see much of an improvement. Again, this thing is doing this so quickly that it's impossible to use feedback while it's flying. All we can really do is observe the end of the maneuver and then modify the behavior so that the following time it works better. That's pretty close to sticking the landing. Very good. For this next demonstration, I want to give you a flavor of something called model predictive control. Okay, we're going to take this vehicle here, and it's got a racket, as you can see. And the racket doesn't have too big of a sweet spot. It's about this big. And what I'm going to do is I'm going to throw a ball at it, and the vehicle is going to fly and hit the ball back to me. We hope. How's it going to do this? Okay, it's going to use mathematical models like we discussed earlier. What it's going to do is it's going to plan a trajectory that will intercept the ball and hit it back to me. Oh, different vehicle? Okay, you're going to switch vehicles? Okay, so I'll explain how the system is going to work and then I'll demonstrate it. Oh, here we go. Looks like it's going to fly. Okay. So should we go ahead with it? Okay. Okay. Not its fault, that was my fault. Okay, so how did it do that? It would use first principles models to plan a trajectory that guaranteed that it would be able to hit the ball back to me. Okay? Then it would execute that plan. 20 milliseconds later, it would reassess the situation and calculate a new trajectory to intercept the ball to hit it back to me. 20 milliseconds later, it would do that again and again and again until it actually hit the ball, hopefully back to me. So it was doing feedback via continuous replanning. This is an extremely powerful concept for doing feedback control because it's very robust to changes in the environment and to changes in the situation. It's constantly deciding, what's the best thing for me to do now? 20 milliseconds later, what's the best thing for me to do now? Et cetera, et cetera. Up until recently, you could only do this type of control for, in process control applications because the dynamics were slow enough on the orders of minutes or hours. But now, because of the confluence of all these technological innovations, we can do model predictive type of control on the order of milliseconds. That means that we can control things in this way over a broad range of applications. For this last demonstration, which we call the Skynet, we're going to use these three vehicles to do something cooperatively. What they're going to do is they are going to propel a ball in the air and then move to intercept it. This is a nice demonstration of various aspects from control theory. The first is optimal control, to figure out the optimal way for them to throw the ball up in the air subject to their constraints. The second is feedback control about these trajectories. And the third is replanning to move to intercept the ball. Okay. So it's definitely worth waiting for. Okay, so the things that I want you to appreciate when you see this is that these vehicles are basically vertical when they're fully extended. The other thing to notice or to note is that the forces that are applied to it are on the order a magnitude larger than the forces that the vehicles can apply themselves. So it's like somebody yanking you with thousands of pounds of force. And they have to be able to coordinate their actions to not only throw the ball up in the air, but then move to intercept it. This is an extremely dynamic task with a lot of uncertainty, with very fast dynamics. Yet, this technique for designing control systems is very robust, and that's why the system works. Great. Okay. Thank you. So hopefully I've convinced you that we have this incredible ability now to create machines that perform incredible tasks. And all the ingredients are there. We have incredible amount of sensing. We can sense anything we want. We can harness power to actuate and make the physical world do what we want it to do. We can bring to bear large amounts of computation to run sophisticated algorithms. And we have the know-how, the theory, the mathematics, to be able to come up with these feedback systems so that they behave in the way that we want them to behave. The thing is, these ingredients are improving all the time. Better sensors, better actuators, better computation, more computation, better theory, and better algorithms. There's one more ingredient that I haven't talked about yet, and I think it could be the real game changer, and that's communication. Right now, machines don't really communicate. If a machine learns something, when it's turned off, it loses that information. What if a machine could learn and adapt and share information with other machines? So let me give you an example. If you could create a machine that did a very complex task, very sophisticated machine, and it took a year for it to learn how to do it, you would never deploy it, you would never build it. But what if you had 1,000 of these machines? Okay? If you had 1,000 of these machines and they could communicate and you had the right algorithms, they could learn that task in one day. Okay? The possibilities are incredible. I mean, think of what we could do if machines could learn together. Incredibly powerful. Okay? And my last note is that it's also incredibly dangerous. Okay? We're creating some pretty powerful stuff here. And it should be clear that it can be misused and it can be abused. Okay? The things that you could do with these types of machines is a little bit terrifying. Okay? So some people advocate suppression, suppress the technology, but that's just not going to work. Okay? You can't close Pandora's box, so to speak. All right? Besides, you know, we as a species are not very cautious. Okay? We're not going to turn our back on these tools that offer so much promise. So instead, we just have to figure out a way to learn how to live with these machines that can do wonderful things, but also very terrifying things. We have no choice.